Okay, so thank you. Yes, so yesterday I essentially presented kind of a, well, let's say some sort of toy example where which I chose so that you see all these principles, all these building blocks from which you can build an LDP for random geometric quantity. And today I want to present or parts of a recent result of Kim, Liao, and Ramanan, who proved a large deviation principle for random projections of random vectors under an asymptotic thin shell condition. So I already mentioned it several times, but let me be a bit more specific now. So previous results before the paper of Kim, Liao, and Ramanan appeared had essentially been restricted to either LPN balls or shut-in unit balls, so the non-commutative LP balls. Yeah? For instance, the whole thing essentially started with a paper by Gantert, Kim, and Ramanan in 2017, where they proved a result for one-dimensional marginals, so random projections of LPN balls into one-dimensional subspaces. Then David Alonso Gutierrez and myself and Christoph Thiele, we considered a higher dimensional version. So we proved an LDP for random projections of LPN balls into k-dimensional subspaces or random subspaces. I presented some of the results from this paper. Actually, in this paper with Joscha and Christoph, we were studying central limit theorems related to LPN balls or high dimensional limit theorems. And as part of it, we also looked at Q norms of random vectors in LPN balls, and some of the results you have seen yesterday. And we also considered more general distributions related to LPN balls. Okay. Then in 2020, Joscha, Christoph, and I, we were able to leave this LP ball setting and managed to prove a Sarnoff type large deviation principle. So a large deviation principle for the empirical measure, more precisely for the empirical spectral measure of random matrices in shut-in unit balls. There you do not have the classical Shechtman-Sinn probabilistic representation, but we proved somehow an analog to this probabilistic representation, and then could prove a Sarnoff LDP. And another paper, which was well, it's from 2020, as of paper by Liao and Ramanan, they proved sharp large deviation principles related to LPN balls and spheres of projections. So that you're not just on the logarithmic scale, but you can get more precise asymptotics. Okay, so this is a non-exhaustive list. Several other results have been proved since 2017, which I do not mention here, and I apologize. Okay. So as I said, in a recent work, Kim, Liao, and Ramanan established LDPs for random projections under some asymptotic thin shell condition, and we'll see what this means in a moment. And what I liked in particular, and I've said this several times, is that their result allows you to deal with alledge balls. So there you do not have a probabilistic representation. So it's not like for LPN balls, you take Shechtman-Sinn and then you're in the game and can compute things. No, so you do not have such a probabilistic representation. You have, as I showed with Joscha in some other paper, kind of an asymptotic probabilistic representation, but not a Shechtman-Sinn type probabilistic representation. And also I should say that the result is somehow restricted to superquadratic alledge balls. So it's not clear what happens in the subquadratic and superlinear case. This is still an open problem, which is quite interesting. Okay, so let me describe the setting. We consider a sequence of random vectors in Rn, and we look at the Stiefel manifold of all n by k matrices well, and they satisfy that the transpose of A times A is the K by K identity matrix. And the quantity we're interested in, or what we're interested in, are the coordinates of the projected random vector. So you have an n-dimensional random vector, you project it onto some k n-dimensional subspace. So it doesn't have to be k. So k can depend on the dimension of the space that you're working in. Okay. So we're interested in studying these k n-dimensional random vectors here. So we project onto a lower dimensional subspace, but this subspace may depend on the dimension. And we assume that well, the random matrix that we choose with respect to the Haar measure and our sequence of random vectors, this should be independent. So as I said, again, the goal is to understand the large deviation behavior of the coordinates of this random vector. And what the authors consider are three different regimes. So first, the constant regime, where you project onto a k-dimensional subspace and k is fixed. There it makes sense. So you have a k-dimensional random vector, and it makes sense to ask for an LDP in Rk. The other cases, where B and C, they concern the sublinear regime, where your kn tends to infinity, but kn divided by n tends to 0. Okay, that's the sublinear growth. Or you have the linear regime, where kn is asymptotically lambda n. So kn divided by n tends to lambda. And since there the dimension of your subspace changes, it makes no sense to ask for an LDP in Rkn. So somehow the natural setting there is to work with the empirical measures. So to embed this into a proper space where you can ask the right question. So this will concern large deviation principles for the empirical measure of the coordinates of my random vector. Okay. So so here we are. So this is the quantity that we're looking at here. So mu n is the empirical measure. So it's 1 over kn, sum j from 1 to kn, delta of the transpose of a and kn, x, and you take the jth coordinate. Okay, so this is your random vector, and you look at the jth coordinate, and this is your empirical measure, the empirical distribution. Okay, so I mentioned that they proved a large deviation principle under an asymptotic thin shell condition. Actually, in the paper, other assumptions appear. So I write here assumption A. You can establish LDPs there. Some other assumptions appear there, but I do not have the time to discuss those. So I'll restrict myself to this condition here, which appears, and this is as follows. So you remember, we just start with some sequence of n-dimensional random vectors, and now we pose a condition on those random vectors, namely that, and this is assumption A, the Euclidean norm normalized by root n satisfies a large deviation principle at some speed Sn with a good rate function Jx. Okay, this is your assumption on the sequence of random vectors. Okay, of course you need some assumption. You need some control over the sequence Xn. And if you like, somehow you may consider this, because this is the Euclidean norm of your random vectors, as kind of a radial contribution to the large deviation principle that we see later when we consider the whole quantity here. Okay, so this is somehow giving you a kind of radial contribution. You will see that later. I'll explain in more detail. Okay, so this is assumption A, that the Euclidean norm divided by root n satisfies the large deviation principle. Of particular interest is also the following. So if, let's say, the speed is n, the speed is n, like a typical speed that you would get from Cramer or so. as n is n, then we call it assumption A star. Okay. This is of particular interest later for the when we look at alledge balls. Okay. So if Sn is n, then we call it assumption A star. Yeah. And one can show now that this assumption here, this LDP assumption, is satisfied for several classes of random vectors. For instance, or distributions. So for instance, for large family of product measures, you need some. I say large family because you need some moment assumptions. A large family of product measures. Or for the uniform distribution on the scaled LP balls for P larger than or equal to 2. That's important. Or for the uniform measure on superquadratic. That's my favorite example, superquadratic alledge balls. Because this is somehow, well, I like it. This is really nice. And if you remember yesterday's talk, just on the side, if you remember yesterday's talk, then you know that assumption A star does not hold for P between 1 and 2. Why? Well, because then we need Sn to be n to the P over 2. You remember my proof where I looked at the norms and then we had these stretched exponential tails. So, but of course, there's still assumption A holds, but with a different speed. So you do not get speed n there. Okay. So these are just some examples. This is my favorite one, which I will show you in a moment. Okay. So what does this have to do with an asymptotic thin shell condition? Somehow I said it's a kind of radial contribution, and you can say yes, okay, because we look at the Euclidean norm of our random vectors, yes, but it's really related to the thin shell condition in an asymptotic way, and this I will just remark here. So say xn satisfies assumption A. Satisfies assumption A with a certain good rate function Jx having a unique minimum at some m in R plus. Then for large n and n, you can show that your random vectors xn satisfy the thin shell condition. Then for large n, xn satisfies the thin shell condition, probability that, well, I should write n here, that the Euclidean norm of xn normalized by root n minus m larger than or equal to some appropriate, well, I can choose an appropriate sequence here, epsilon L, and this is bounded above by epsilon L for a suitable sequence epsilon L, which tends to 0. So for all L in N, there exists some NL such that if N is larger than NL, then I get this. Yeah? And this is why I somehow call this an asymptotic thin shell condition. Yeah? If we have a unique minimum, then you can show this. Yeah? So the takeaway message, if you have this radial assumption, let's say, radial assumption A plus unique min, yeah, then you have an asymptotic thin shell condition holds. Yeah? And that's why we say we prove a large deviation principle under an asymptotic thin shell condition. Yeah? So this in a sense, well, need some more space, sorry. So this in a sense gives the following picture. So the following similarity to the CLT setting. So on the one hand, we know by Clartak's CLT that thin shell implies the CLT, and the large deviation counterpart somehow is asymptotic thin shell. Asymptotic thin shell implies a large deviation principle for empirical measure. For the empirical measure in the sublinear and linear regime. Okay, so all right, sublinear and linear. Yeah, so this is somehow the takeaway message. Yeah? This radial assumption, this LDP I impose on the Euclidean norms, if this is combined with a nice enough rate function, then this is really an asymptotic thin shell condition, and this allows me to prove a large deviation principle for the empirical measure of the random projections of my sequence of vectors. Yeah? Okay, so the constant regime. So as I said, in the constant regime, when you project on a k-dimensional subspace, then you can prove an LDP in RK, and the question makes sense, right? Because you project onto RK, and then you can prove a large deviation principle there. So K does not change with N. So the theorem that Kim, Liao, and Ramanan proved in this case, this is only part of it. They also get under some other assumption something else, but I restrict myself to this, let's say, simpler case. So K is an N fixed, and you assume that the sequence of random vectors satisfies the assumption A star. Yeah? So we have an LDP with speed N and some good rate function Jx. Yeah? Then you can show that the normalized projections of your random vector, the normalized random projections of your random vector, satisfy an LDP in RK at the same speed N that comes from assumption A star with the following good rate function. The good rate function is IK, which is given by the infimum over all C between 0 and 1. You get the rate function somehow coming from assumption A star, and you get some other rate function. Yeah? Some interplay between two rate functions, one obviously coming from the radial assumption. Yeah? So I want to say that this is somehow the radial contribution, yeah? Radial part or radial contribution of the LDP. So if you're not familiar with the previous results of the authors, or in particular of Gantert, Kim, and Ramanan, then you do not recognize this here. Yeah? If you are familiar with it, then you know that this here, this is the rate function that you get when you look at a random vector uniformly distributed in an LPN ball, and you project it onto, I don't know, the first coordinate direction or onto a random direction. This doesn't matter. And then, and P should be 2. So you're on the Euclidean ball. Yeah? So if you look at, I write it like this. This is what you get from looking at x. I write it like this, xn2. You take a random vector uniformly distributed on a Euclidean ball, and you project it onto the first direction, let's say, yeah? Or on a random direction, doesn't matter. Yeah? And this here, yeah. And this is if you prove an LDP for this quantity, then this is the rate function you get. This is why I'd like to say, okay, well, this is a radial part. For me, this here is a spherical part, a spherical contribution or an angular contribution, yeah? Okay. Yeah. And how exactly this enters, you can see from the proof. If I have time, I will sketch it. Yeah, but heuristically, this is already, if you look at this somehow, of course, you expect some contribution coming from this radial part. And if you think somehow of assumption A as thin shell, that you're in a sense, the mass is concentrated on a sphere, yeah, or on some shell there. Then you also want to see some angular part, right? Want to see some radial part and some spherical contribution. And this is exactly what you get. Okay, but now let me first before I sketch the proof, if I have time, let me take a look at an example. And this will be the example of superquadratic alledge balls. That you can. So what we're going to show is really that if you take random vectors uniformly distributed on a properly scaled alledge ball, then they satisfy assumption A star. Okay. So let's take a look at this case. So let V from R to R plus be an alledge function. That is what? Well, it should be convex. It should satisfy it's 0 at 0, and it should be symmetric. V of x equal V of minus x. Okay, and assume that this is a superquadratic alledge function, yeah, and assume that V is superquadratic, which means just that V of x divided by x squared tends to infinity if x tends to infinity. Particularly, this is satisfied if you have a two convex alledge function. Okay, so this is an alledge function, and what is the alledge ball? The alledge ball is defined as follows. We define BVN to be the set of all x in Rn, such that the sum I from 1 to n, V of xi is less than or equal to n. Yeah. So this is the find the alledge ball BVN as the set. If you take, let's say, if V of x is norm x to the power p, and p is larger than 2, yeah, because, well, I'm in the superquadratic case, then your BVN is nothing else than the scaled LP ball, okay? So your alledge balls or your alledge spaces, alledge balls are generalizations of your LP balls. Yeah? But usually they're it's more delicate to deal with them because they're not homogeneous and so on. Yeah, so this really looks like a simple generalization, but it comes with a lot of difficulties. Yeah. Okay, so this is the alledge ball, and now one can show the following. So one can show, and I'll give the idea. I'll sketch the proof because this is quite nice. So one can show the following, that if xn n and n is now uniformly distributed, well, let me write it like this. So if xn is uniformly distributed on BVN, on our alledge ball, then the sequence of random vectors on alledge balls satisfies assumption A star, with good rate function. Well, good rate function J, I write x comma v because it has contributions from my I write it like this, and this is as follows. I write it. This is J of 1z squared. I'm not going to say what this is. This is one part of the rate function, because this would take too long to introduce this properly, but this is some part of the rate function plus the supremum less than 0 of s minus the log of the integral over r e to the s alledge function dx. So this is a good rate function, and it has a unique minimizer. So one can show that this holds, and that jxv has a unique minimizer. The point why you get this kind of expressions is somehow that the uniform distribution on an alledge ball is somehow related to certain Gibbs measures. So you get these exponential parts here. And this contribution here, this comes from the volume of the alledge ball, this thing here. So you take a vector uniformly distributed on the alledge ball, then it satisfies assumption A star, and the rate function has two contributions somehow, and one here you will see in a moment. This is exactly what comes from the asymptotic volume of an alledge ball. And this is because of the proof. This is well, you'll see. So to sum up, you can show that xn and n satisfies the asymptotic thin shell condition. The asymptotic thin shell condition. Okay. So they fall into the framework of the theorem that I've presented. So this is nice. So random vectors in alledge balls, uniformly distributed, satisfy the asymptotic thin shell condition, and that's why I can deduce some large deviation principle for the random projections. So what's the idea behind the proof? Idea of proof is as follows. And the key step is the following. If A is some measurable subset of R, say measurable, and you define the quantity B2Vn, the set of A, to be your alledge ball intersected with the following set of all x and Rn, such that the sum xi squared is in A times n. Then it's immediate that the probability that 1 over n I from 1 to n xi n squared is in A. This is the right? We're interested in this. We want to establish the asymptotic thin shell condition. Yeah. So we want to, in the end, we want to understand this expression, right? Yeah. So if I look at this later, I will contract. I'll use the contraction principle. Yeah. So I can take the root here. So this probability here is essentially what we're interested in. That's what I'm saying. And this can be expressed as a volume ratio. That's and this is just B to Vn of A divided by the volume of the alledge ball. And now you see why the volume or the asymptotic volume of the alledge ball is essential here, or how this appears. Yeah? Because if you take then the log, then you get these two parts here, these two separate parts. So what you have to do once you expressed your tail probability in terms of this volume ratio is you have to understand the large deviation behavior of this part here and of this part. Okay, so you need to understand the asymptotic logarithmic volume of an alledge ball, and you need to understand this. But essentially what you need to do is you need to understand this, because if you take A, the set R plus, the positive real line, you get this. Yeah? Okay, so the goal is then, in the second step, to understand, to analyze the large deviation behavior of this volume here. Yeah? So step two, step two is analyze the large deviation behavior of the volume of B to Vn of A, yeah, let's say. Okay, and what you see is somehow that from this you get this rate function J1 comma something that appears. I'm not going to show any details, but where is it? From this you get this contribution. And next, but which is essentially the second part, you need to determine the logarithmic volume, the asymptotic. Yeah. So, but I still write it. Determine asymptotic log volume of BVN. Yeah. So what you show is that that the limit, as n tends to infinity, 1 over n log the volume of BVN, this is minus the supremum over s less than 0, s minus the log of the integral over r e to the s v of x dx. So this is where this contribution in the rate function comes from. Okay, yeah, so you can just on the, maybe I mentioned, so independently of the authors, Zaha and I also proved this result, and we also obtained the sharp asymptotics for the volume, by using sharp Crumier large deviations. But this is what the authors did here is a very nice trick. Yeah. Okay, so now you have the large deviations for this. You have the large deviation behavior of the volume of BVN, and then you just put things together. Yeah, I write it like this: put things together. Then you get put things together and obtain an LDP for, now we need to be careful, for this quantity, right? xin squared. Yeah, this is almost what we want. With speed n, and good rate function, which I presented, yeah, but well, good rate function J1x minus the sup s less than 0 and so on. This is the same. And now what you need to do, we saw it yesterday several times, you just contract. So you use principle 2, you know? And then you use principle 2 with x maps to root x, okay? And then you get the large deviation principle for this quantity. That's what we're interested in. It's the Euclidean norm normalized by root n. And here we get x squared. Yeah? So this follows from the contraction principle. Okay. So this is essentially how you, I mean, the details are delicate, right? There's some computations you have to do there, yeah. But this is how you show that uniform random vectors uniformly distributed on all H balls. The Euclidean norm normalized by root n satisfies an LDP at speed n with a good rate function that you can explicitly write down somehow. Okay, so how much time is left? It's not much time left. So I'll probably skip the sketch of the proof. I'll include it in my notes. I mean, I also updated the notes from the other lectures, and maybe the organizers can upload them to the webpage, or someone can do that, right? So you can. I added some details also to talk 1 and talk 2, if you're interested. Okay, so this was the linear regime, and instead of sketching the proof, I'd like to. Well, I'll add this later. I'd like to talk about another result, and this concerns part B that I mentioned for the sublinear regime, and it's a essentially it's a Zanoff type large deviation principle, and it reads as follows. So assume now that we have not fixed k, but our kn grows sublinearly with n. Yeah? And that assumption A holds. Remember, assumption A said that the Euclidean norm divided by root n satisfies an LDP at speed Sn, not n, okay? Sn, any Sn. And some good rate function Jx with a unique minimum. Then the authors proved the following. Depending on how the speed of your LDP for the Euclidean norms, for the radial part, is relative to the subspace dimensions, you get a different answer for the large deviation principle for the empirical measure. And it's as follows. If the speed is faster than, goes faster to infinity than your subspace dimensions, then the empirical measure satisfies a large deviation principle on the space of probability measures. You can generalize this to the Q-Wasserstein topology. I'm just staying in this setting here. At speed Kn, with good rate function being the relative entropy. If Sn is equal to Kn, then mu_n satisfies an LDP with the same speed Kn, but the rate function is the relative entropy plus this here. This is coming from assumption A. If your speed is slower than your subspace dimensions, then mu_n satisfies an LDP with speed Sn, Sn with a slower speed, with good rate function essentially coming from the radial part. So remember, mu_n is this empirical measure. If I would essentially tell you, look, this is the quantity we want to study. This is the quantity we want to study. Then you might guess that, okay, this is somehow 1 over Kn, j from 1 to Kn, delta something. This is some Zanoff type contribution. So what I would like to see in the LDP in the end is the relative entropy appearing in some sense. But then on the other hand, somehow you have you have here these random projections. These random projections somehow they come from assumption A. So I want also to see a contribution from this part. This is this Jx. And sometimes you see only one, and here you see two. And this is again essentially what I said yesterday, largest exponent wins principle. So you see the LDP of the slower speed. Look at this part here. Here, this is only the Zanoff part that you see, because Kn is less than Sn. This is our Sn. This is what assumption A brings you, this speed. And here we assume that Kn is less than this. So all you see is this. And this is something coming from Jx, because somehow this is you get instead of an LDP for the Euclidean norms of speed Sn, which you have with rate function Jx, you can also get one with Kn here, and then you get some other degenerate rate function, which is only 0 at the minimum and plus infinity everywhere else. So you get some here. There's a degenerate part contributing, but essentially you see just the Zanoff contribution. Here everything happens at the same speed, so both contribute. You see this contribution here coming from the radial part, and you see so this here, and you see the Zanoff contribution. And this is an interplay between both. Okay, because they occur at the same speed. And now the last case where Sn is much less than Kn. Well, so Sn, this is the slower speed somehow, because this is the Zanoff speed in a sense. This Kn, this is now slower. So essentially what you see is just the radial part and no Zanoff part. Only in a degenerate way does it enter here. Okay, so without entering any proof somehow, looking at this quantity, you might guess, that something like this happens. This is only very heuristic, but this is somehow the feeling. You look at this, and you might guess that this is something that happens. Same speed, you get an interplay, and then slowest speed wins somehow. This is what you see. Okay. So I have 2 minutes. I'd like to at least to explain to you what this has to do with the Gaussian here, because this is, I wrote it here, gamma sigma denotes a Gaussian distribution with variance sigma squared. Because I explained to you why the rate functions look the way they look in a sense, but I somehow did not tell you why, what it has to do with some Gaussian contribution there. So what's the idea? And then I'll stop. The idea is as follows. So you can show that mu n, your empirical measure, is equal in distribution to some other measure, which is of this form. You take the measure of a set and you somehow scale this set with what I write here. This is what I mean. xn2 norm with mu n tilde being the following empirical measure. It's the empirical measure of root n a n k n 1j. So you take the jth entry in the first row of your random matrix. Okay, and this you can show. Okay, so you have the quantity we're interested in is related to this empirical measure here, but since an kn 1, so this is just the, well, let me write it like this, j from 1 to k, this is equal in distribution to these Gaussians. These are standard Gaussians, kn, divided by the Euclidean norm of the full vector. Okay. This is because the vector of the first k elements in the top row of an orthogonal random matrix is in distribution equal to this part here, and then you know that the top row is uniformly distributed on the sphere. Yeah? And since you know this, then you know that your mu n tilde is equal in distribution to some nu n tilde, which looks as follows: kn delta root n gj, and here you take the full vector. And this is, you can show, exponentially equivalent. Remember, principle 3, which means that if you can establish an LDP for what I write now, then you have one for mu n tilde. This is exponentially equivalent to mu n given by 1 over kn, j from 1 to kn, delta gj. And this is somehow where your Gaussian contribution comes from, because this thing here satisfies an LDP at speed kn with good rate function. So LDP at speed kn with good rate function being the relative entropy with respect to the Gaussian measure with sigma equal to 1. Yeah? And then you use contraction principle and you build your LDP for this thing here you're interested in. Yeah? But this is how this Gaussian contribution enters here. Yeah? And there somehow. Okay. So time's up, I see, and I'll stop here.